Good morning, family. Good morning, everybody, and happy Sabbath today. A good morning to our teachers. A good morning to all our parents at home. A good morning to all our students. I say good morning to all my listeners and a good morning to all lovers of knowledge across the globe. I'm welcoming you once again to another exciting and educative edition of School on Air Physics for today. This is your favorite and interesting program you can only find on Oxygen FM 96.9 on frequency modulation herewith. The station that inspires, the station that informs, the station that ignites. I'm your regular host, Kenny BADMUS. I welcome you once again to another exciting edition of School on Air Physics. On behalf of the management and the production crew of Oxygen FM 96.9, situated at the Knowledge Hub 121-123, Obafemi Awolowo Okeado Ibadan, I welcome you all to this exciting and transformative edition of School on Air Physics for today. At Oxygen FM 96.9, our guiding philosophy is deeply rooted in education, enlightenment that illuminates the mind from lesson to another lesson. I want to say a big thank you to the entire production crew behind the scene for the smooth delivery of our academic presentation every week. So, I want to say a big thank you to Mrs. Tokumbo Ishola, the head of station, my studio manager, studio engineer, Miss Floriana. I think, I'm happy I'm getting used to the name, and particularly my production manager, my producer, Mr. Femi Ogunyejo, who is very vibrant and committed to making my delivery smooth every week. I remain your host, Kenny BADMUS. I want to introduce you to another topic for today. Very interesting as usual. It's a continuation of what we've been doing, we've been bringing all along. We want to make sure that we open every chapter and ensure that all details, all concepts that are peculiar are deeply presented in very defining concepts to make it very understandable to all our students at home. Today, we are focusing on dimensional analysis. Dimensional analysis, like I said. So, what is dimensional analysis? What is dimensional analysis? So dimensional analysis is a method. It is a method in physics that we use to derive a relationship between physical quantities. It is a method that we use in physics to determine the relationship between physical quantities. It's also a way to check whether equation is dimensionally correct. It is a way to check whether equation is dimensionally correct. We also use it to convert units from one system to another. So we also use it to convert units from one system to another. So invariably, it is a 3-in-1 approach. It is a 3-in-1 method that is used to determine relationship between physical quantities. It is used to check the correctness of equation dimensionally, and also to convert units from one system to another. We have 3 basic dimensions, fundamental dimensions in physics: the physical quantities of length, mass, and time, which are we are familiar with, rather. So I want to say that the three physical quantities that we are used to in physics is the physical quantity of length, mass, and time. So the length has the symbol m. Also the dimension is m. The physical quantity of length has the symbol of L, and the dimension is also L. So the mass also has a symbol of m and the dimension m. So time too has a symbol of t and the dimension is t. There are other quantities which are derived from these three basic dimensions. So there are other quantities that we can derive from all these three dimensions, like I said. So what are the principles, the basic principle behind the dimensional analysis? So the dimensional analysis is a way to ensure that physical equation must have the same dimension on both sides. If I say distance is velocity is distance over time, what I have on the right hand must be the same as what I have on the left side. So in terms of dimension. So that is a way of trying to get a relationship, with velocity over time. I'm sorry. So once again, like I said, we are trying to see that distance is velocity times time. So the dimension on the left side, which is distance, is L, while the right hand side, which is velocity times time, is L times L divided by T. Rather, it should be multiplied by time. When L over T, L divided by T is multiplied by time, we will equally have length, which is L. So the dimension on the right side is equal to the dimension on the left side. So that is the principle of dimensional homogeneity. So that is the principle of dimensional homogeneity. So what are the applications of dimensional analysis? What are the applications of dimensional analysis? In dimensional analysis, we use it to check the correctness of equations. We use the dimensional analysis to check for the correctness of equations, which I have mentioned earlier. 2, we use it in finding dimensions of unknown quantities. So it is a way of finding dimensions of unknown quantities. We use it in converting units between different systems. We also use it in converting units between different systems. So we derive relationships among physical quantities. If you go back to the definitions, these applications are easily derivable. So it's a way of deriving relationship among physical quantities. However, it has limitations. So it has limitations. What are the limitations of dimensional analysis? Dimensional analysis cannot prove that an equation is physically correct, only that it is dimensionally consistent. So it is the dimensional consistency that dimensional analysis offers, but the physical correctness is not ascertained. It cannot prove that. It cannot distinguish between quantities, like quantities with the same dimension, like walk and talk. They have the same dimension, which is m L raised to power 2 divided by T raised to power 2. So their dimension is the same. So the dimensional analysis method cannot distinguish whether this is walk or this is talk. It only gives it dimensional consistency. Also, it cannot determine the numerical constants such as pi, such as exponential e. So these are not determinable by dimensional analysis. So even the integers of 2, 1, half, and the rest, there is no clear dimensions attached to them. Let's go to dimensions of common physical quantities. The common physical quantities of velocity, acceleration, force, work or energy, power, pressure, momentum, and density. What are the dimensions of these physical quantities? Velocity, which is by formula distance over time divided by time. So we know that distance dimensionally will be L, and it will be divided by time t. So invariably the dimension is L t inverse, L t inverse, or L over t. But appropriately we write it dimensionally as L inverse t. So then we have acceleration, which is velocity divided by time. Having gotten velocity before, we know that velocity is L inverse t divided by t again. So then we have to inverse t. That's to give us L t inverse squared. L t inverse squared. So that is acceleration. Then we have force. If we have force, which is mass times acceleration. So m for mass multiplied by L t inverse squared. So going by the fact that we have been able to define dimensional analysis of acceleration as L t inverse squared. So then we have force as mass times acceleration. Force is mass times acceleration, which is m L t inverse squared. Then when we have work or energy, that will give us in terms of formula as force times distance. So our distance remains L, and from force that we have derived earlier, our force is m L t inverse squared times L, which is distance. L now becomes L squared. So let's work it out, students. Please, m L t inverse squared times L will now give us m L squared t inverse squared. That's how best to write it dimensionally. So this time, if you are saying divided by t squared, that says that's the fact that we are trying to put up the formula. But dimensionally, we write it m L squared t inverse squared. Then we come to power. Power is work over time. Having gotten work earlier as m L squared T inverse squared divided by time T again, which is T. So that is the formula. But dimensionally, it will be M L squared T inverse cube. Do you get that? Power now becomes M L squared T inverse cube. So because work originally was M L squared T inverse squared divided by time T formula. So the dimension will become M L squared T inverse cube. Then we can go to pressure. We can move forward to pressure. Pressure is force over time. Force over area. Force over area. We now split it. Area is length times breadth. Length and breadth is L times L. So we now have force, which is M originally, having defined it earlier on. Our force is M L T inverse squared divided by L squared. L squared resulting from length times breadth. So invariably, one L will give way. So there will be one L length remaining at the denominator. So we now have pressure as M L inverse T inverse squared. So pressure is M L inverse T inverse squared. Then we can also move to momentum. Momentum is velocity times mass. So momentum is mass times velocity. So mass represented by M and velocity. Having done that before, we have L inverse T. So mass times velocity, which is momentum, will give us M L T inverse dimensionally. So momentum is M L T inverse. Let's move on to density. So in density, formula says density is mass over volume. For mass over volume, we have mass at the numerator to be M. Volume will give us length times breadth times height, which all the three being L. So that is M divided by L cube. So now dimensionally, we have density to be M L inverse cube. Density is M L inverse cube. So like we said in the principle of dimensional homogeneity, so what we have on the left hand side, like density now, so what we have on the left hand side must be the same as what we have on the right hand side dimensionally. So what we have on the right hand side must be the same as what we have on the left hand side. So, welcome back. Let's now check. Let's check whether V, an equation, which is equation of motion, that V equals to U plus AT. Let's check how dimensionally correct it is. So we can see its velocity is the same velocity plus AT. So let's now check for the correctness. Having done that earlier, that velocity is distance over time and the dimension gives us L inverse T. So all these being added together, what do they give us? So our concern is by separation we try to define each of them. So what does the U give us? So the U give us L T inverse or L inverse T. But AT this time is acceleration times time. Acceleration is L T inverse squared. Let's go back to our original derivation. Acceleration is L T inverse squared. We now multiply by time t. So multiplying by time t, 1t will give way on that inverse. It will now remain 1t on the inverse. So we now have L T inverse. So that is to check for the correctness of this equation. All the terms have the same dimension, so the equation is correct. So also you can check for the correctness of force is equal to ma, having derived it earlier. So we now consider mass times acceleration. Mass times acceleration, it's more of a repetition, but with pen and paper or using Newton's second law, that F is equal to ma, we now try to check for the correctness of our dimensional analysis as given earlier by m L T inverse squared. So this time now say m mass times acceleration, m for mass and acceleration, having gotten that earlier as L T inverse squared. So our force remains the same as m L T inverse squared. So that is how to check for the correctness of the dimensional analysis, to ensure that what we have, that is, it is homogeneous. So the same thing we have on the right hand side is what we have on the left hand side. Having been given that force is ml T inverse squared dimensionally, so we now use the force, the Newton's second law of motion, which is F is equal to ma. We now try to derive it dimensionally by multiplying dimension of mass and the dimension of acceleration together. So a repeat of the applications of dimensional analysis, it is a way of deriving relationships between physical quantities, 2 or 3 more. It may be between and among physical quantities. So we derive relationship among physical quantities. We convert units between different systems. The dimensional analysis, we use it in converting units between different systems. Also, we use dimensional analysis in finding unknown quantities. So if there is a new formula that comes up now for anything at all, so we come together, we put them together, we put the dimensions together to make up one dimension, trying to derive the unit. On dimensionally, we're trying to derive dimension for that particular quantity which is unknown. So, and we check for the correctness like we did now. We check for the correctness of equation. So we use dimensional analysis in checking for the correctness of an equation. Yeah, welcome back. So let's go back to the checking for the correctness of these equations by way of verification. So we have an equation of motion that says that S is equals to ut plus half at squared. So the equation says that S, I think the distance is ut plus half at squared. Now we want to verify the equation. Having known that S, that is the distance, dimensionally is L. So then, to check for the correctness, let's consider at squared. Since we have to leave out the half. So A, which is acceleration, is L t inverse squared. And we have time t, which is square to at squared. So t squared now. We can now realize that there is an inverse t squared and there is a t squared. The two cancels and we have L. We have L. So that is by verification that what we have originally on the left hand side, S for S, which is L, is the same thing as what we have on the right hand side, which is L. So L dimensionally, L on the left hand side is the same as the right hand side, L, which is for ut plus L for half at squared. So the two together remains L. L is for L, whether the plus or anything. So the dimension is correct. So let's equally check again for pressure. When we have P to be F divided by area, that is the force divided by area, like we did the other time. So we know that pressure will give us the same thing what we have on the left hand side earlier for pressure. Is what we want to verify. So having done it originally, that M L inverse multiplied by T inverse squared. So we want to verify again that is it correct. So force, like we know, is M L T inverse squared divided by area. The area remains L squared because area is length times breadth. So the length, breadth, they are both length. So L, length for L, breadth for L. So we have area as L squared. So pressure has M L inverse squared divided by L squared. So if you transpose the S squared that is on the denominator to the numerator, we have it to be M L inverse and T inverse square remains. So that shows us the correctness. So we can also do that similarly for density. So if you do that for density, it will give us the same. Density rho is ML inverse cube. And we know that density is mass divided by volume. And our volume is all about L. Volume is length times breadth times height. The length is for L dimensionally, breadth is L dimensionally, height is L dimensionally. So volume is L cube. Now we have the formula as mass divided by volume, which is M divided by L cube. That is the formula. So dimensionally, we have it as M L inverse cube, M L inverse cube. So that is how to verify it. So we can also do that for momentum. We can also do that for momentum. So for momentum, we have it originally. Momentum as P, which is mass times volume. So M for mass remains sacrosanct, and we have that of velocity as L T inverse. So joining them together, we will have M L T inverse. Now let's go to something a little bit complex, something that looks complex. So in complexity, we have the gravitational constant. If you want to find the gravitational constant from the Newton's law of gravitation. So the Newton's law of gravitation tells us that F is equal to G m1 m2 divided by r squared. That is the radius, the distance separating the two mass objects. So by change of subject of the formula, if we have F as G has been equal to G m1 m2 divided by r squared, so we try to cross multiply. If you cross multiply, just take that step, you realize that F will multiply r squared, and it will give us G, which is the gravitational constant, multiplied by m1 minus 1 minus 2. So divide both sides by m1 m2. If you divide both sides by m1 m2, you will have the gravitational constant standing alone, where we now have G has been equal to F r squared divided by m1 m2. So that is the formula. However, dimensionally, we want to get it dimensionally. So dimensionally, we have the force. Our force is M L T inverse squared. Force is M L T inverse squared multiplied by the radius, which is same as distance, and this time it's raised to power of 2. So L raised to power 2 divided by mass 1 and mass 2, both being m and m. So if you take your time to write it down, you now realize that we have 1 m at the numerator and we have 2 m at the denominator. So 1 will cancel and 1 will retain. So I will transpose 1m to give us m inverse. M inverse L now cube and T inverse squared. So we have gravitational constant G as m inverse L cube and T inverse squared. Now, for dimension for torque, however, we now open the studio line for conversation. So please, the studio line is open on 07047003969. Studio line is 07047003969. 07047002969. 07047002969. Studio line is open. So we have the dimension for torque. And torque is T distance, or r, let's say r, which is the radius, times force sine theta. We may have to vary the sign, for us to get the consistency. So let's leave out the sine theta, and concentrate on torque as a function of force times perpendicular distance from the pivot. So force times distance. So, and the step one is that we write down the dimension of the force, which is m l t inverse squared. So, and the second one is that we multiply it by the distance, which is represented dimensionally by L. So that we now multiply them all together. So we have M, we have 2L this time. So L squared, T inverse squared. Studio line remains open, 07047003969. So having multiplied them together, the dimension remains valid, and it is M L squared T inverse squared. And the SI unit is in Newton meter. So let's think of another one. So dimensions for centripetal force. For centripetal force, we have the formula as mv squared divided by r, which is the distance separating the mass bodies. So if we want to derive the dimension for F, which is the centripetal force, M for formula FC, giving us mv squared divided by r. So let's go back to our original derivation, where we have the mass times velocity, and this time velocity is squared. What is velocity? The velocity dimension is L inverse squared. So M multiplies L inverse squared, bracket open and close for velocity, or squared, and divided by r, which is the distance, which is given dimensionally as L. So we have FC to give us M L squared T inverse squared divided by L. You can see from the numerator that we have M L squared T inverse squared. Okay. Hello? 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 Yeah. So in continuation, we have M centripetal force as M L squared T inverse squared divided by L. On the numerator side, we have 2L, which is L squared, and the denominator we have L, single one. So we can cut one with another, so leaving behind only one at the numerator. So FC, which is the centripetal force, giving us as M L T inverse square. That is the dimension for centripetal force. In summary, we have been able to derive dimensional the dimension of a few physical quantities in physics, and we are able to do that for velocity. Do that for acceleration. Force, work or energy, power, pressure, momentum. Did for density. Did that for centripetal force. We did that for gravitational constants, and it's all confirmed for its homogeneity. So if invariably we cannot get our colors due to few hiccups, maybe so, because I can see a strange course coming in. So towards the end of this program, I want to say a big thank you again to the entire production crew, from the head of station down to my producer, Mr. Olufemi Ugunyejo. I remain your host, and towards the closing, I'm bringing today's edition, exacting edition of School on Air Physics, to a close, and hoping to see you next week on another exacting edition. Thank you for your time. Have a pleasant day.